So in this video, we're going to be extending our discussion of recursive time complexities. We've already seen the method of explicitly solving for an amount of work across a recursive tree. We generalized the work to every level, we drew a general bound, and then we created a strategy. If every single node in the tree does constant work, we bound to the amount of calls in the tree. So why did we do that? Well, let's imagine what the bigger picture here is. The bigger picture is when we were trying to bound iterative algorithms, we just had for loops, and we could easily understand how much work is done in the for loop. So remember back to this. When we're trying to bound this for loop, what is the bound? If we know that the work in the for loop is going to be constant time, then we're just counting the amount of for loops, right? So we're actually doing the same thing with the general bounding approach that we've seen before. We're counting the amount of calls in the tree, or we're trying to do a blanket bound and approximate the amount of calls in the tree, because we're doing the same thing as we're doing here. Now, the reason that this is a very confusing topic initially, and it's difficult to even draw bounds in the interview, is because if it's a really hard recurrence to solve, where work varies a lot at every node, it's much harder to understand what each call is doing. If we imagine recursion as a for loop, if every one of these nodes is a for loop iteration, all we've done is solved the simple answer. We've been solving simple questions. Because this for loop does n iterations, each iteration is constant work, so we bound to linear time. And then what we did was we said, let's imagine that this recursion that generates 2 forks at every node is going to do constant work in each call. The depth of the tree is n, so we bound to a rough approximation of O of 2 to the n calls. So basically what we're saying is the amount of for loop iterations is upper bounded to 2 to the n. Because we're just saying, imagine these are the constant time for loop iterations. Every one of these calls is an iteration, basically, and it's doing constant work. It's just formatted as a tree. So this is the bigger picture of where we're going, and this is the bigger picture of the questions we're asking. If we only know this, we're not well tooled to really solve harder time complexities and harder recurrences without doing the actual math. The way to skip over and not do that is we need shortcuts. And this is one shortcut. We have one shortcut in our pocket, which is generalizing to count the recursive calls. And then from there, we can bound each recursive call. But this is an approximate approach, and it only counts calls. If we're doing linear work in each one of these calls, then we're in trouble. We need to adapt because the subproblem size will change, and we can't just say, I'm doing for loop iterations with constant work. We can't just say, I'm counting calls with constant work. We can't do that anymore. So we need general strategies to identify, given this recurrence, given this behavior, given this algorithmic approach, what will my time complexity be? Is this reasonable to approach or reasonable to do? So we're going to look at a couple of those. We're going to look at some generalizations. You won't need to solve anything, but it's just a given that if your code behaves like this, your time complexity will bound to this upper bound. For the first one, we're going to look at a recurrence we already know. Here's our first generalization. If we are splitting in half and we're doing linear work in every call, then the bound of this is going to be big O n log n. And where have we seen this before, and why is this true? Well, we've seen this before with merge sort. Remember, merge sort, 2 calls, input split in half, merge subroutine does linear work. What does merge sort's recurrence look like? It looks like this. That's merge sort's recurrence. 2 calls, split the input in half in every recursive call, and in the merge subroutine, we're going to do n-1 comparisons at worst. And if you want to see the details of that, you can go see the merge sort video. But right now, we're just worried about time complexities. And this n-1, that's just linear work. So we can just generalize that and say linear. All right, and what we see here is actually exactly what is seen there. 2 recursive calls, input split in half, linear work. This C is an arbitrary constant. And that means the work is going to be linear. By definition of big O, constants disappear. So this is big O of n. Merge sort's recurrence is n log n. And when we solved merge sort's recurrence in the merge sort video, we did the exact math. And we saw that there were a ton of messy constants in the front. They just disappeared. And n log n was a dominating factor. Where does this play into generalization? If you have a problem and you see that you can split it into halves, and you see that you can make 2 recursive calls to solve the first half, solve the second half, and you know that you're going to do linear work to merge the results when they recursively come back, then that means your algorithm will run in n log n. Merge sort satisfies this recurrence, and now we understand if two calls, input in half, linear work, in every call to merge these steps, to merge the results, as we saw in merge sort, merging, that is going to lead to n log n time complexity. And you wouldn't even need to solve anything. It's just this class of time complexity. If you solve the tree, no matter what that C becomes, it's not going to change the dominating factor. Our time complexity will still bound to n log n. So now let's look at the next one. So Q calls with half of the input plus linear work within each call. So what does this mean and where would we see this? One case of this is in recursive multiplication. We won't get into recursive multiplication because it's an academic topic. It's not really useful for the interview, but you will see this recurrence in that context. The algorithm that we learned in grade school to multiply integers together was an n-squared algorithm. And we won't prove that here, we won't do the math here, but what happens is you're going to multiply the 8 with everyone, you're going to multiply the 5 with everyone, and then you'll do some additions. And this can be improved using divide and conquer. And again, I want to stress, if you're trying to think of a divide and conquer approach, these will help you reason about how fast your algorithm will run. Initially, you could turn this into a 4 recursive multiplication subroutine with linear work. Again, we won't worry about how this actually works, we won't worry about that. We're just going to worry about what Q is, the amount of recursive calls. And remember, in this case, Q is 2. We're always going to be generating 3 calls, 4 calls, 5 calls, or more. We can't be generating 2 calls. We already covered that case with the previous recurrence. What is this going to evaluate to? This evaluates to big O of n to the log base 2 of Q. And now I don't want you to get scared by the logarithm. Don't be scared by that. We know what logarithms mean. Logarithms are asking a question. What power do I need to power 2 by to get Q? Initially, let's look at this recurrence. This recurrence is going to look like this. This recurrence is going to look like that. It's going to look like 4 recursive multiplications where n is the length of each number. It's not the length of all the numbers, it's the length of each number. Here, n is 4. We're going to do 4 recursive multiplications with each a smaller piece, n over 2. So n over 2 there, plus linear work. Now, what does this mean in context of this? We can plug it in. Okay, and now, what does that become? Log base 2 of 4. Again, don't be scared by the logarithm. It's asking us a question. 2 to the what is 4? 2 to the 2 is 4, so it's just n squared. And so without doing any math, and I actually did another video where I did do the math for this problem, but without doing any math, we just used this generalization that holds true for values of Q, and we just plugged in to this. And the reason this is true is because people already did the math. They either use constructive induction, which is something you probably won't need to know for interviews. They use the tree method, something else, and they notice that this always holds based on the dominating factor. So big O of n squared. And what happens is there's actually a different type of multiplication called recurrence multiplication, which breaks it down to 3 multiplications. Multiplications entail recursive calls, so we want to minimize that. But the additions are fine. The additions stay to linear time. What does the recurrence then become? We're making 3 recursive multiplications, and again, we won't worry about the details. We're going to cut each input into the recursive multiplications will be half the size of an original number, and linear work in terms of additions. So now let's solve this equation again. So 2 to the what is 3. And this approximately equals 1.58. You wouldn't need to know this off the top of your head, but we can just write that. And so the reason I don't want to stress about details is I want this to be a way of thinking for you, because if you see a problem where it's really natural to divide each side into an input, and it's really natural that the base case is the solution, for example, sorting a left and right half, a single item is the solution. No items is the solution. Those are both sorted. In the case of merge sort, if we just divide, and then we know an efficient merge subroutine, it's really good to model that in divide and conquer context. And these recurrences allow you to think about that more efficiently. Think about what does it mean to make 3 more calls? What does it mean to split in 2, split in half? So now we've seen this, and we saw how we changed it to n to the 1.58. And this is called recurrence multiplication. It uses 3 recursive multiplications, a few more additions than the original method, But there's actually a faster way of addition that runs in n log n time that was actually discovered in 2019, but we won't go over that here. Now let's look at the final generalization that we can take away that will allow us to eyeball a lot more recurrences and not have to solve anything. So now here is another recurrence. We have t of n is less than or equal to t of n over 2 plus cn, which that's just linear work over there. So what is really happening here? We actually have already seen this form. It's just in this case, q is 1. It just doesn't exist there. It just means we're making another recursive call with half the input. But in every level, we're making an amount of linear work. What would this look like? This would look like this. At the top level, we would start with n. How many subproblems? One subproblem. How much work would we do? We do linear work. So let's just imagine we do n minus 2 in work. And the next level, the size of the input is going to be n over 2. How many subproblems do we see? We see one subproblem. How much work do we do? Input size is now n over 2, and then we still do the minus 2. Remember, the work in the actual recursive call is a function of the input size. Here, the input size changed. And let's do this one more time for it to sink in. N over 4. How many subproblems at this level of the recursive tree? But in this case, it'll just be a linked list. One subproblem. And then the subproblem size is n over 4, and then we subtract 2. And if we really wanted to, this is actually a pretty simple one. We could just draw a summation. So we could sum over the levels. How many levels would there be? Since we're dividing in half every time, we can express this logarithmically. And if we really wanted to do that, we could do a summation. So this is summing the work from the 0th level up here to the second to last level right before the base case. What the ultimate generalization we can draw is how many subproblems. We're going to do 1, 1, 1, 1, 1. There's just going to be one subproblem at every level. And then how does the subproblem size change? Well, in this case, it's 2 to the 0, 2 to the 1, 2 to the 2. So then it's 2 to the I. You can put this in any calculator online, and what you'll ultimately find is that the answer is going to be linear in time. So recurrences of this shape, where we're splitting in half, linear work at every level, is going to be linear in time. And this is actually familiar. Remember how quicksort's recurrence kind of looks like this? In the average case, quicksort's recurrence looks just like mergesort's recurrence, 2t of n over 2 plus some linear work from partitioning. And then we saw the algorithm of quickselect. We used the quickselect algorithm for the kth largest element problem. The kth largest element could be found by partitioning, choose which way to go, cut input size about in half, partition again, go in the next direction, partition, go in this direction, partition, and the recurrence for that was this. The recurrence for the quickselect algorithm in the average case, or the best case, is going to split the input in half, and we're going to do linear work. And we're going to only make one more recursive subcall to go in the next direction after partitioning. So this solved to linear time. And we found that was a really good approach. And in the worst case, we would rarely ever pick bad pivots every time. Worst case would bound to quadratic time. But in this case, in the best case, and in the average case, as it also turns out, it bounds to linear time. So this is another helpful recurrence to think about. If we split it in half and we see that we're doing linear work at every call, we're going to have linear time. And it's just one recursive subcall more. So that's exactly what this one looks like. So let's wrap this up. So in this video, what did we see? We saw how we could solve other types of recurrences. We looked first at the recurrence of merge sort, 2t of n over 2 plus linear work. Then we looked at recurrences where q is greater than 2. We looked at fast multiplication, 4 recursive calls, 4 times t of n over 2 plus linear work. And then we looked at how if we change it to 3 multiplications, it improves. And finally, we looked at what we see in quickselect algorithm, splitting the input in half, making one more recursive subcall, and doing linear work in each subcall. So these are 3 recurrences that happen very often. You're going to see this a lot, and it allows you to solve things faster when you're first thinking and devising your approaches. And this doesn't cover everything for recursive time complexities. We've covered how to count the amount of calls in a recursive tree, and that actually gives us the time complexity if every call is constant time. We've covered generalizations on recursive calls. We've covered how to solve recurrences using the recursive tree method in our approximation video. But there's a lot more you can do with recursive time complexities. It gets much harder with randomization. And again, you could have like summations that you have to solve, and it gets much more difficult. But I hope this was a good primer to, this is going to cover a good amount of interview problems. So I think this will suffice for probably 60 to 70% of problems you'll see. And then the rest are probably in a much tougher echelon that are much harder to figure out on the spot. This was recursive time complexities, an extension on more common generalizations, and we're going to get more work with recursive time complexities as time goes on.